Let's talk about force and potential energy. And using the shorthand notation, for every conservative force, there exists a potential energy formula. And I am using capital U for potential energy. So for example, if the gravitational force, assuming that the acceleration due to gravity is relatively constant, then we can use mgh plus some constant here for the potential energy formula. If we are dealing with gravitational force where little g is not relatively constant, then we have negative big G mass 1 mass 2 over r plus some constant. And you'll notice there's always a plus constant. It should be addressed in another video that you can always add a constant to the main formula. If you're dealing with elastic force or spring force, ideal spring, then you got 1/2 k delta x squared plus c, and an electric force, which is not for physics 251 or 151, we have the electrostatic constant times the product of the charges divided by the distance plus some constant. We're also dealing with that fact that conservative work with the calculus definition is equal to the negative change in potential energy. And so therefore, if we integrate the left-hand side and sort of turn this into an integral, then we end up with the integral from some initial to a final condition of some differential, and so we end up with this. Assuming the conservative force is parallel to the change in r, we can sort of deal with the dot product on that side, and ultimately we end up with that the force is negative du dr in the direction of r. So if I have the potential energy, I can find the force that is involved with it, or more specifically, I guess, the conservative force in some particular direction. So if we make it slightly more generalized, if I'm dealing with I, j, and k hats, corresponding to the x, y, and z direction respectively in this case, if it's a one-dimensional problem, then f sub x is negative du dx I hat, and so forth. If we're in more than one dimension, then we basically have to deal with derivatives in other directions, and so I introduce the nabla, and it's an upside down delta with a vector symbol over it. This is known as a vector operator. So we have this nabla is equal to I hat del del x plus j hat del del y plus k hat del del z. And notice you have a gap there because it operates on u. So if we had this negative nabla u, then there'd be a u here of which you're taking a derivative. And for those who have had it, this is also the negative gradient of u. So for example, if u is equal to 5x squared plus 2x minus 3, then the force involved is negative I hat du dx, which is negative I hat, and then just do a derivative, 10x plus 2. If we have x and y, so we're now dealing with 3 dimensions here, then we have negative I del u del x minus j hat del u del y minus k hat del u del z. And when you're doing this, this is known as a partial derivative, and the mechanics of it are incredibly simple. The fact that you assume that anything that is not the differential on the bottom, so anything that's not x, is a constant. And so we have only one variable here, if x is my variable, and so it becomes 10xy. Here, you assume z is a constant, so it's 2z, and there's no x there, so that drops out. As opposed to the straight up derivative, if I was doing du dx, then this would be 10xy plus 5x squared dy dx, and so on. That's just the first term. So with a partial derivative, you assume that any of the other variables with respect to x do not change, and so those terms drop out. And so we have negative I hat times this, negative j hat times that, minus k hat times this, and that's basically, if you have the potential energy formula, how you find force.